Good morning, all, and good afternoon to our friends joining from China, and warm welcome to everyone across the world. It is an honor today to have Professor Roger Cracknell with us, talking about his work in designing fuels and engines for optimum efficiency. Thanks everyone for joining our fifth technical webinar this year. First, let me share my screen. First, let me very briefly introduce our agenda today. So after the introduction, we'll have 15 minutes for Professor Cracknell talking through in details of his work around this topic. And following the presentation, we'll have the panel discussion with Professor Hong Mingxi, who is our president of UKCSAE, Dr. Jing Qiao from Chang'an Automotive, UK Research Center, and Dr. Haiwen Song from Jiangling Motor. During the event registration, we have collected quite a range of questions for everyone, and you're welcome to send me new questions to the UKCSAE host in this meeting. We'll try to answer as many questions as possible. So for the new friends joining our event, let me give you a introduction to our society. UKCSAE was founded in 2002 and formally registered in UK as a non-profit organization last year. We are trying to connect the Chinese community of automobile industry in the UK and promote exchange and support among its members and associated partner organizations. We plan to host annual industry level summits, regular online, offline technical seminar like this one, as well as the networking events. We currently have over 350 active members from over 50 companies and organizations across the UK and China. For more details, if you're interested in us, please visit our website, www.ukcsae.co.uk. Just reminding you, besides of this excellent event, having Professor Roger Cracknell with us, we'll have some upcoming events which you might be interested. On 8th of August, we'll have our 6th technical webinar. Topic will be around ADAS software architecture, simulation, and sensor evaluation. We have two distinguished guests from Jaguar Land Rover UK, Dr. Gorman and Dr. Ding Renxiao, presenting their work around this topic. In September, October, we're planning to have our annual conference, also attending the Global Auto Talents Annual Conference and Auto Industry Innovation Forum. Okay, that's about me talking. Let me hand it to Professor Hong Mingxi to introduce our distinguished guest, Professor Roger Cracknell.
Hello, everyone. Welcome again to this webinar of the UKCSAE. And so it is our pleasure today to have our speaker, Professor Roger Cracknell. And many of you perhaps already know Roger. Roger obtained his PhD from Imperial College in chemistry in 1994. And then he joined Shell, work until today. Now he appointed as principal science expert within Shell. Roger is a fellow of Society of Automotive Engineers, which is SAE International, and you probably know that we don't have too many fellows at in the UK from SAE, so that's good recognition of his work. He's also fellow of Royal Society of Chemistry, and he's a visiting professor in a number of universities, including Leeds University. He is an honorary professor at the University of Birmingham, Department of Mechanical Engineering. He's also a member of the International Board of Directors of the Combustion Institute. And Roger has published a number of papers with SAE and also other academic journals. So Roger has been active in the research field of fuels and engine combustion for many years. He is giving us a good support, especially today, giving this talk on design fuels for engine high efficiency engines. So let's welcome Roger to start his presentation. Okay, thank you, everyone.
Yeah, Roger, I'm handing it to you. I think you're on mute.
Yes, thank you very much, Hongming, for that kind introduction, and thank you very, very much to the UKCSAE for inviting me to give this talk. So I hope you can all hear me okay.
Yes.
I'm now going to start to share my screen, so please
Yes.
shout if you can't hear me. So I think I can't share my screen at the moment. Let's see what I can do. Now I can do it. Can you see my slide?
Yeah.
So my talk's going to be really in two parts today. The first part will be just giving a bit of background to fuels development in the context of the energy transition and reaching net zero carbon. And then for the second part, I'm going to be talking about a couple of projects that I've been involved in looking at engines with advanced combustion systems, so that by the end of the talk, I'll have covered kind of both facets, the designing fuels part and then the designing engines part for optimum efficiency. This is a standard slide that all Shell presentations come prefaced with. And the basic meaning of this is that we're going to talk about scenarios, we're going to talk about what might possibly happen in the future. But bear in mind that these are just scenarios. They're not guarantees of what will happen in the future or guarantees of future investment decisions. So please don't make any investment decisions based on what I'm about to tell you. So we'll start with the first part of my talk, which I've called the pathway to zero carbon mobility, where really we talk about all of the what needs to be done in terms of fuels as we move towards net zero carbon. And the first place to start is that the world needs more and cleaner energy. And energy and mobility is key to people's prosperity as well. So we're likely to see the global population increasing from where it is today to about 9 billion by 2050. But at the same time, there will be inevitable stresses on the environment, especially climate change and also air quality as well. So we have to find a way to develop a low carbon future that works for all of the world's population. The transition is underway, but there's a long way to go, and there are a lot of significant challenges ahead. Shell has got a history of producing scenarios, and after the Paris Climate Change Agreement, it launched a new scenario called Sky, which looked at everything that would have to be done in order to limit global temperature rise. And I think the Sky scenario was originally assessed as being limiting global temperature rise to 2 degrees, but we've subsequently modified it so that with additional reforestation, it would be consistent with a 1.5 degrees C temperature rise goal. Now, this is just one version of what would need to be done. But I think the conclusion is that you need to do virtually everything in terms of the levers that you need to pull to actually get the world towards a net zero in terms of sometime later this century, which is essential for that. Now, different parts of the world will reach net zero at different times, and obviously many of you are familiar with the fact that the UK and the European Union has committed itself to net zero by 2050. But this recognises that different parts, different regions will operate at different paces. I think that if you look at what happens to energy, and this is the diagram over here, and energy sources, that the world will still be using a significant amount of oil and gas, even in 2050. And so we need to find a way that we can actually deal with that, and that liquid and gaseous fuels will still remain, particularly in hard to electrify sectors. So this is a real challenge, but we need to do a little bit of everything. Within Shell itself, we've made a number of commitments. First of all, we've made a commitment to be net zero from our own operations by 2050. So this is, if you like, the scope 1 and scope 2 emissions. But bear in mind that when you produce a fuel, say you're using it for operation in a gasoline vehicle, that on a well-to-wheels basis, 20% of the emissions come from producing the fuel, but 80% of the emissions come from burning the fuel, from turning the gasoline into traction at the wheels. And so what we've done is to actually have an ambition for the whole of the well-to-wheels process. So our overall net carbon footprint ambition that also includes the combustion of the fuel as well. So we've got an ambition to reduce the overall net carbon footprint of our products by around 30% by 2035 and by 65% by 2050 compared to a 2016 baseline. And bear in mind that this is principally our customers' emissions rather than Shell's emissions. This is an extremely ambitious prospect. So in terms of some of the things that we think need to be done, and the truth is that you need to do everything. Obviously, one thing you can do is just to make everything more efficient. For example, flare reduction. Natural gas has a role to play as well, because the CO2 produced per megajoule of natural gas is much lower than from oil. You've got renewables, you've got wind and solar, something which is extremely important. You've got biofuels, and Shell's already one of the world's largest biofuels producer, but this is something that needs to continue as well. The shift towards electric mobility, particularly for passenger cars, is again part of the important part of the story, and I think a key part for the early part of reducing CO2. There's also carbon capture, utilization and storage. Whether you're doing direct air capture of CO2 or whether you're just finding more dense sources of CO2 and sequestering it in geological or other formations. And also something that doesn't get talked about that much are natural sinks of carbon, so nature-based solutions, reforestation. And I'll talk about that a little bit more as we go through. Now, it's important to understand what is meant by net zero. It means that there are some greenhouse gas emissions that are emitted, but at the same time, you're using carbon and sequestering it. And in the end, you end up with net zero. So examples are using carbon in roads, and these are some standard slides, but I guess that's a reasonably appropriate one, and showing I think that's the carbon being stored in the roads in Beijing. Then there's geological storage, including sequestration, and there's also land use change and reforestation, which we'll talk about a bit more in a minute. So you emit carbon, but you also use it and sequester it as well. And this is really the concept of net zero. And talking a little bit more about nature-based solutions, you've got a number of reforestation partnerships. It's important to also have a proper market mechanism for dealing with the carbon credits that you get. And you may have noted that in the UK, you can actually, if you go to a Shell station, you can actually opt to have your emissions offset. And this is through a number of accredited projects. So in terms of some of the reforestation partnerships that we're involved in, there's an agreement that Shell has got with Forestry Scotland to plant 1 million new trees in Scotland. In the Netherlands, I can't pronounce this too well, but the Stadsbosbeheer forest, 5 million new trees are going to be planted in a partnership with Shell. And last year, Shell was involved in a project where 300,000 trees were planted in Spain. So this is an important part, we believe, of achieving our net carbon footprint ambitions. Then, obviously, we've got low CO2 fuels, and I'll talk a bit more about each of these in a minute in its own way. But biofuels, so we're talking both conventional or first generation biofuels, which can still significantly reduce the well-to-wheel CO2, and also advanced biofuels as well. Hydrogen, particularly green hydrogen, but also blue hydrogen if it's combined with carbon capture and storage. Electric mobility, obviously, ideally from green electricity. And then I mentioned also the use of natural gas, which, although still results in CO2 emissions, because of the nature of the methane molecule, you get less CO2 per megajoule than you do with crude oil-based fuels. So if I put everything onto a single diagram in terms of pathways to zero carbon mobility, if you start with renewable energy sources on the left, either in the form of green electrons from wind or solar, or you start from biomass, you've got a number of options for where you get to on the right. And those options on the right include green electricity, green hydrogen. But also you can produce hydrocarbons as well through either a power to liquid, power to gas route or via biofuels. And we'll discuss a number of these pathways as we go through. First of all, let's talk about e-mobility. And this is something that Shell has made a significant number of investments in, both, if you like, in the upstream part and in the downstream part. So in the upstream part, Shell's actually an operator of a large offshore wind farm, the Borssele 3 field in the Netherlands. And it's looking to participate in other large offshore wind projects. There's the Silicon Ranch solar PV project in the US, and getting involved in solar is again part of the strategy. As we'll talk about in a minute, there's also involvement in a number of renewable natural gas projects as well that can then end up giving you obviously electricity, and electricity that's essentially green if it's come from natural gas, which is renewable. Shell also provides electricity to customers, both business customers and domestic customers as well. And it allows you to have renewable electricity because we participate in the REGO, or the Renewable Energy Guarantee of Origin scheme, that allows that energy to be certified as renewable. And then in terms of charging your vehicle, Shell owns a company called New Motion that provides charging solutions in the home, in the workplace. And this is a smart charging option, so that what it's able to do is it's able to look at the demand of the grid and then balance that out so that it smooths out some of the demand for electricity for home electricity refueling, and gives the customer effectively a better price for their electricity, which they use for charging their electric vehicle. At the same time, Shell in Germany has invested in a battery company called Sonnen, which smooths out the electricity demand in people's houses through having batteries in their houses. So that's charging at home or at work, but also Shell provides fast charging solutions for people when they're out and about. So there's Shell Recharge, which is typically around 100 kilowatt refueling. And Shell is also a partner in Ionity with a number of large car manufacturers, and has installed the Ionity systems. And this allows for ultra fast recharging. I think it's 350 kilowatts, so you can charge vehicles in approximately half an hour. So Shell's involved in all of the elements of e-mobility. If we look at other aspects of this diagram as well, if we switch from e-mobility at the top to look at biofuel options at the bottom, Shell blends an enormous amount of biofuel into fuel already. So approximately 9.5 billion litres of biofuels are blended into gasoline and diesel. Most of this is conventional biofuel or first generation biofuel. And we've got a large joint venture in Brazil called Raízen, and so Shell actually is one of the largest biofuel manufacturers as well in the world. We invest, as I'll show in a minute, in technologies in which waste can be converted into biofuel, and I'll discuss some of those projects in a minute. But I think that even with first generation biofuels, the key thing is really to ensure the sustainability of the feedstocks for those biofuels. And Shell's involved in a lot of these kind of partnerships throughout the world to ensure that that biofuel supply is sustainable. To give an example of some of the advanced biofuel projects that Shell's involved in, if we look at the waste chemicals project in Rotterdam, which is with Enerchem and some other partners, and the idea then is to produce biomethanol from non-recyclable waste, and that could then in turn be converted into gasoline by a methanol to gasoline process, but there are also plenty of uses for methanol as well. Shell has acquired JC biomethane in Oregon, and this will produce a significant amount of natural gas from agricultural waste through anaerobic digestion, and actually producing biomethane or renewable natural gas, whatever you want to call it, is one of the lowest capex ways to produce advanced biofuels. We're selling in Germany and some other markets a certified renewable fuel, a diesel containing up to 33% of certified renewable components, which derive from waste and residue. So we guarantee a well-to-wheel CO2 saving of 20%. So this is a partnership with VW, Bosch, Neste, and some other companies as well. And finally, the other thing I'd like to talk about is something called IH², which is where we've taken a technology from the Gas Technology Institute, and this is an efficient conversion route by taking woody biomass and other woody residues and allowing a production of a number of transportation fuels from that. So a lot of projects and a lot of interest in that. Hydrogen. We're one of the founding partners of the H2 mobility project in Germany, and the ambition of this was to have a network of 400 stations by 2023. And this is one of the examples of a public-private partnership. It's probably fair to say that at the moment, that it's the classic sort of chicken and egg problem, that the infrastructure is there, but there aren't so many fuel cell vehicles that actually use the retail stations. But it's not just Germany. It's also throughout the world. I think we've probably got the largest number of hydrogen retail stations in Germany, but we've got 3 in the UK, and we've got others under development in the Netherlands and Luxembourg as well as a reasonable number in the US and Canada. And these are constantly being added to in terms of the number, so that this is the sort of latest map, but I had to get an update yesterday because the numbers are always changing. Hydrogen is also being used in other ways in refineries, because a lot of the well-to-wheel the well-to-tank energy in a refinery to produce fuels is often associated with hydrogen manufacture. So we're involved in a project called REFHYNE, where we use the world's largest PEM electrolyzer. So this is from ITM Power in Sheffield, and this is installed at the Shell Rhineland refinery. But converted that hydrogen to either synthetic natural gas or to a power to liquid type fuel, you'd massively further reduce the well-to-wheel efficiency. And actually you'd end up with an efficiency that was lower than using fossil diesel or fossil gasoline routes, which are the ones shown for comparison in the middle there. So I think, although there's a lot of talk about needing to produce synthetic hydrocarbons so that we can still carry on using internal combustion engines, I think we've also got to be a little bit realistic in terms of the losses of the energy that you get when you do that. And actually, that's why in many respects it's better to use green electricity directly in a battery electric vehicle. But if we do make synthetic fuels, there's a reasonably high technology readiness level for doing that, because that's something that Shell's history, Shell's been doing that, developing the process of GTL since the early 70s. We've built a world-scale plant in Qatar about 5 years ago, and this follows on from a commercial scale plant in Malaysia about 25 years ago. So hopefully that gives you an overview of all of the pathways to zero carbon mobility. I'm now going to move on to talking about new combustion concepts. And I think you've got to bear in mind that if you look at my last comments on battery electric vehicles, not all parts of the transportation infrastructure is it particularly easy to electrify. It may be possible to electrify passenger cars where range is not the critical parameter, but it becomes much more difficult to electrify heavy duty transportation, for example, when to actually achieve an acceptable range. The amount of lithium-ion batteries that you would need on board would be very detrimental to the amount of goods that you could actually carry. Likewise, also aviation and marine. So I think it's really important to make sure people are clear in terms of what mobility they're actually talking about. So the things I'm going to talk about now could be applied to passenger cars, but they could equally well be applied towards heavy duty transportation as well. And I think we need to look at and I know I've got many people from car OEMs on the call, so apologies for this if I'm teaching you things that probably you're already very familiar with. But we perhaps need to think more broadly about traditional combustion concepts. I think that a few years ago there was a view that really you could divide it into three: spark ignition, compression ignition, and then you had this perhaps slightly new type of combustion concept in which you had a homogeneous charge, like in spark ignition, but actually this was ignited through compression ignition, and this came to be known as homogeneous charge compression ignition. But since then it's become a little bit more complex, in that people found that pure HCCI isn't particularly practical, because it's very difficult to control the combustion phasing, because it's purely controlled through the chemical kinetics. And if you've got subtle differences in intake air pressure, or subtle differences in the auto ignition reactivity of the fuels, that you end up with an inability to control the combustion phasing. So with the desire to control the combustion phasing, people developed concepts either approaching from the compression ignition side or from the spark ignition side, which would perhaps help do that control. So starting with thinking from the spark ignition side, those of you, well, what if you put a spark in there? And the idea of having a spark in there is that you will provide just enough increase in pressure and temperature so that you will get the remaining part of the charge to auto-ignite spontaneously, so that actually the combustion phasing is then controlled by the spark. And this traditionally is known as spark-assisted compression ignition, or SACI, but there are various other acronyms, and certainly, as we'll see in a minute, that Mazda, for their SkyActiv technology, have chosen to call this SPCCI, or spark-controlled compression ignition. The other approach to this is starting from the compression ignition side, so that you don't have a completely homogeneous mixture. You have a mixture that is partially premixed, so that the combustion phasing is still controlled through the injection timing rather than through the spark. And this is known as partially premixed combustion. And there have been a lot of other embodiments of that. So it's quite exciting that we live in a world in which some of these concepts are actually appearing in vehicles, and certainly the Mazda actually make quite a lot of fuss of their SPCCI combustion system, in which you do get this spark to actually assist with the HCCI. But there is another way of looking at PPC as well, and that's looking at this concept, and that's from the PPC side. And so a goal has been to get these types of engines to work on market gasoline, and certainly you can do that with SACI and SPCCI, but you can also do that from a partially premixed combustion standpoint as well, and this is known as gasoline compression ignition. The challenge with this is to get the gasoline to ignite at low load, because gasoline is designed to be resistant to auto ignition. And so this is often done with having some combustion assist, although it is also done with a rather complex valve train arrangement and rebreathing as well in some embodiments. So we've been involved in a couple of PPC projects recently that I wanted to just highlight. And this is a one through Concarway, which is the European Oil Company's Environment and Science organization in Brussels. This was a Horizon 2020 project, and also involved NEN, the standardization arm, or the Dutch standardization arm, who are also part of CEN, and also involved Peugeot as well. And a bespoke engine was designed with spark assist. But again, this comes from the kind of PPC side, in which the combustion phasing is still controlled through the injection timing, and the spark is there just to overcome some of the challenges of low load. And this was quite exciting, because we found in this engine, when we plotted our results on an ISFC map, that we actually got quite a large peak efficiency region with an ISFC of less than 200 grams per kilowatt hour over quite a broad region. Unfortunately, when you needed the spark assist at low load, the efficiency really dropped off. And so that's why I think in terms of taking this forward as a concept project, we're thinking about either looking at cylinder deactivation, which is clearly one way of avoiding those low load regions, or hybridization, again, so that you largely avoid operating in those low load regions, because that really drags down the drive cycle efficiency. But it shows that this type of technology really does have the capability to be able to achieve very high efficiencies. And so I talked about this at last year's Aachen colloquium, but we have a paper for the 2020 SAE Powertrains, Fuels and Lubricants. So this meeting was due to be in Poland, but it is now virtual. And I think what's really important is that this technology was able to run with pump gasolines. So we tested a range of gasolines between RON 92 and 98. So US regular gasoline, standard European gasolines, various ones, and they all worked okay in this project because they had the spark really to help smooth out some of the different auto ignition characteristics. But if you went to 102 RON gasoline, then we had a little bit more of a problem. But that's something that isn't standard. But this does work on standard pump gasoline, and that's something that's important. Another project that we've been involved in looking at partially premixed combustion, which has recently been published, is some work with the Technical University of Eindhoven, in which obviously I mentioned earlier that Shell is a very large producer of ethanol. How well will ethanol work as a dual fuel within a dual fuel? So the idea of this was that you have port fuel injection of ethanol and direct injection of diesel in a, when we wanted to test it in a unmodified single cylinder DAF bench heavy duty engine without any reoptimization or recalibration of the engine. And in terms of energy, we were able to put up to 80% of ethanol through the port to get it to ignite. So we found that we got, obviously with ethanol in the port, we got a more advanced CA50. We got, unsurprisingly, faster combustion because it's much more premixed. I should say that the codes A10 and A70 are tell you it's at 1200 RPM, but it tells you the percentage of full load. So 19.9 bar was 70% of full load in this particular engine. And yeah, you can see that at low load, the burn duration gets slightly longer. That's just because everything is over mixed. But at most other conditions, you get faster combustion because of the increased pre-mixing. And you get definitely lower soot emissions, as you probably might expect from using ethanol as a dual fuel concept. And you get slightly different effects with NOx, but it's not working so badly. The challenge is, I think, hydrocarbons and CO at low load, because you've got over mixing, and this is a kind of consequence of, or a risk of, partially premixed combustion at under these conditions. But I mean, I think there's a belief that if we can get fast enough light off in an oxycat, that this is something that's not a showstopper. And what's quite interesting is that this was done, as I say, just without recalibrating the engine, and it was accompanied, apart from the lowest load, by an increase in efficiency, just because we are getting faster combustion using the partially premixed arrangement. So this is something that was really encouraging. So we got dual fueling with ethanol up to 80%. It ran without too many issues. We got higher efficiencies. It's just the emissions. We got lower soot. The NOx was generally the same. It's just this higher CO and hydrocarbon that was a little bit more of a challenge. So this just shows that we were active, and I could have highlighted a lot of different things that Shell's involved in, looking at engines and fuels and trying to get them to work together. We're a partner in the US Optimum program, for example. I could talk a lot more. I could have talked about Octane, but I thought it was useful just to highlight a couple of projects on the advanced combustion, looking both at partially premixed combustion, just to show what is possible. Anyway, I hope that probably is all I was going to talk about, and I hope that was interesting to everybody. And obviously, I'd be happy to answer any questions or do that as part of the panel session. So I'm going to stop sharing now.
Well, thank you, Professor Cracknell, for your presentation. Yeah, so let me introduce our panelists for the next section. So now let's dive into our panel discussion. So we have Professor Roger Cracknell from Shell and Professor Hongming Shi from University of Birmingham and Dr. Jing Qiao from Chang'an UK Research Center and Dr. Haiwen Song from Jiangling Motor. So if you don't mind, Professor Cracknell, I will kick off with some questions we collected from the audience, and then all panelists are welcome to join in the discussion.
Okay.
Yeah. So I think one of the quite high-level questions, which I'm also interested, as I'm not a fuel design kind of background, is how do you tackle the emissions from the for the new fuel designs from in the design phase? How do you kind of plan that, and then with the target in mind, and then design a specific fuel to just tackle the emissions aspect of it?
In a sense now, the emissions, certainly the local air quality emissions, are very much determined by the after treatment that is on the vehicle. So it's really just ensuring that the fuel is compatible with the latest after treatment. So if you look historically, that the introduction of three-way catalysts I think prompted the phase out of lead in gasoline, and also for example having SCR catalysts or lean ox traps prompted the reduction of sulfur in diesel and gasoline. So the emissions are pretty much determined by the whether you're Euro 6 or China 6B or whatever the vehicle is. Now, there may be some impact, say, on particulate emissions if you don't have a GPF in a direct injection vehicle, and certainly I think that if you reduce the final boiling point of the fuel and have lower heavy aromatics, that can make a difference to that aspect of it. But in the past, before three-way catalysts, the composition of the fuel used to have much more of a significant impact of what came out of the tailpipe. But if I'm honest with you, it doesn't make so much of a difference anymore. That's not to say that there's no difference whatsoever, and that's one of the advantages of people who use, say, a paraffinic diesel fuel like Shell GTL, that you do get reduced NOx and PM, or at least a better NOx PM trade-off, and that can also be advantageous as well, because it can help reduce engine out emissions, because obviously even if your after treatment system is able to deal with the emissions through a particle trap, if you have less engine out soot, then you control the back pressure in a better way, and that also improves efficiency. And also, soot is obviously, if your combustion is producing soot, then it means that less of the energy within the fuel is going to do useful work on your piston. So there is some impact that the fuel has, but on sort of air quality, but it's perhaps not as great as it used to be.
Okay, thank you for your answer. Any comments for our panel?
Maybe I could.
Okay, Roger, that's a good point, that after treatment made such a difference to the emissions at the tailpipe. Perhaps the design of the fuels now is more for let engine working in different combustion mode, for example, octane number or certain number, mix of both, and to change the auto-ignition temperature so that the compression ignition on PPC or SAC, as you said earlier, that can be applied with different compression designs. How do you see that is going to carry on, or whether that is practically applicable in future products?
I think that the challenge is, I mean, and I would say, perhaps to add to my previous answer, I would say the other thing, and this is some work we've been involved obviously with you in Birmingham, is the importance of cleanliness in the engine in reducing emissions, and that's a key formulation attribute of fuels, is to make sure that the injectors are kept clean, because often it's deposits that can also lead to emissions as well, and also that leads to efficiency loss. And we've done quite a lot with Birmingham with yourselves on that, which has been really important. I think with things like gasoline compression ignition, the challenge for introducing this type of technology in the market is that you've got to use a fuel that is already available. And I think there's a desire, certainly from the European oil industry, to address the MoGas distillate imbalance. So basically, that's kind of refinery speak for saying that refineries in Europe, at least, tend to produce more gasoline than they need and less diesel than they need, and especially needing to produce distillate fuels for marine use. A lot of refineries are not operating in an optimal way. They're really maximizing the amount of diesel type fuels they're having to produce for various uses. I mean, that was certainly the pre-COVID situation anyway. And so there is a desire to be able to run more gasoline, to be able to use gasoline in a more efficient way. But the problem is that if we say, well, okay, a vehicle needs a special grade of fuel, then you end up with this chicken and egg problem, that people won't necessarily buy the vehicle unless they're confident that they can get hold of the fuel, and people will be reluctant to sell the fuel unless they're going to sell a decent volume of it. So you end up with this problem. So that's why it's much more desirable that you can operate the vehicle on a fuel that is readily available. And I think if I talk about Hong Ming's contribution in this, I think that you were the first to coin the idea of dieseling, of kind of combining gasoline and diesel, so that you've got a fuel that is much easier to auto-ignite than gasoline. And I think that has some merits, because both gasoline and diesel are available on the forecourt. I think one of the challenges, and this is something our Konkawi group has been looking at, is the danger that you could end up with a flammable mixture in the fuel tank. But as long as you have a mixture that is predominantly gasoline, that doesn't seem to be as much of a concern as we thought it might have done. But there are some papers coming out on that. And this is an interesting concept. But I think probably on the whole, I would say that you need to be able to get the technology the vehicle technology to be able to operate on the gasoline that is commonly available in the market. And that was why we, as Konkawi, conducted the experiments that we did, testing a number of market gasolines. And if you have some sort of combustion assist, then you can make the engine operate on a range of different gasolines. I think it's more challenging if you're trying to just get auto ignition through getting the right temperature there, and you're having to use internal EGR or rebreathing in some complex cam profile just to get the heat up. I think that's much more difficult.
Thank you. I think that it's clear more work now is moving to make gasoline compression ignition widely researched nowadays. Yeah. As Cotton has told us many times, and there's more gasoline to be consumed rather than diesels.
That's true.
Okay, Dr. Chao Jun.
Yeah, I think now, Roger, thanks very much for that comprehensive seminar. So before I start to ask engine questions, I'd just like to maybe discuss a bit about the bigger picture. I think while we look at how to make energy efficient and all that, we can't ignore the fact the climate is changing. You know, the target of achieving 2 degrees look increasingly more difficult. And I think Shell's great work on the scenario, how to achieve 2 degrees, that's all excellent work. And also your company transform yourself from an oil company towards this diverse energy providers. Well, that's a great effort. The first question is, how are you going to make money? I'm pretty sure most of your profits still come from oil, while you use the oil money to pay for the solar panel, all the rest. Great work, but I guess at the end of the day, as business, you still have to somehow work out a way of make profit from those new ventures, if you like. It's not easy job. You know, all this biofuel, all this second-gen biofuel, all the rest, I think is a lot of great research. So the question really is, how do you turn that great research into a business you can sustain? The first question. Second question is, you know, great about all this third mode of combustion, whatever name you call it. What we see from industry is light duty, the electrification would take a part of it. I think the Shell scenario would say the same. But before we got more electric cars, there's probably a lot more hybridization going to happen. The question really is, hybridization really adding cost. So what we like is the engine very cheap. What the other research you've done, those engines perhaps getting high efficiency get quite expensive. So that may not be kind of aligned with the kind of hybridization, if you like. So just those two questions, if you could give you a comment, please, Roger.
Okay. I mean, the first question is how can Shell still thrive through the energy transition? And obviously, this is a really important question. I think what I showed is that if you look at electric mobility, for example, Shell is involved in all stages of that. It's investing in wind farms, it's investing in solar. It's also invested so you can get your domestic electricity from Shell through Shell Energy, and you can buy renewable electricity from Shell. And then Shell is involved through New Motion in home recharging, and effectively that does sort of smart grid operation. So it's a smart recharging. Shell's also involved in a domestic battery company in Germany, and also when you go and recharge at a Shell station, whether it's Ionity or it's a Shell recharge, then you can always go into the shop and buy some excellent coffee in there as well, and help Shell's business. So I think if you look at electric mobility, there are kind of many ways that it is possible to provide a business model there. But I think it's also true that the number of vehicles on the road, number of passenger cars, the assessments I've seen that they still seem set to double to about 2 billion by 2050. So it's not clear that the number of cars with internal combustion engines will probably reduce very quickly on a global basis. It might reduce much more quickly in a country like the UK, in which internal combustion engines may get banned in 2030 or 2035, and new internal combustion engine vehicles. But across the world, there will still be a demand for oil and gas products as well. So if you look at that combined with technology in advanced biofuels as well, I think that it's more of a question of diversification. So I mean, I think that there is a belief that people will still need mobility, and the point is for customers to have a trusted partner that they can use to help be their provider for fuels for mobility. You ask another slightly more difficult question around hybrids. Obviously, I think that you may want a more the simplest sort of internal combustion engine technology, and this is something quite interesting that I think we've given a lot of thought to fuels for hybrids. I would say also that it's not just in some of these advanced combustion modes, it's also what octane requirement will there be, because if you're going to be operating at the best point all of the time with your hybrid engine, that may well mean that you may want a higher compression ratio, so not something more complex. So there may be an interesting octane discussion to be had also around fuels for hybrids as well. I think it's a point well made. It depends, I guess, on the trade-off between how important it is to have the most efficient internal combustion engine. What I would say is that with gasoline compression ignition, if it's difficult to operate at low load, it does mean that they are more amenable to hybridization. And I'm not sure necessarily that they're going to be any more complex than any other system. I think that because it doesn't need a really complicated cam timing. It's really just to a large extent, as I understand it, just a modification of diesel technology. So we shall see.
No, it's good. I'm not saying that you know, the problem with the research of all those.
Yeah, no, it's a good question though,
Yeah.
because.
Go on.
But it may also be that this type of system becomes applicable also for heavy duty engines as well, and that's another.
I think for heavy duty, absolutely makes sense. You want to do gas ethanol with diesel or heavy duty more towards natural gas, like what's happening in the US. I think the light duty really difficult for engines because you got potentially hybridization that want a cheap engine. We also want a high efficiency. So we pay a lot of attention to Nissan's sort of e-power type of thing. Maybe you run the engine at specific points that are very efficient, but don't run a wider range. So maybe you can make some sort of a compression ignition, whatever, make it easy. So low operating range engine may be a way to go. So, but we have to.
I mean that is one of the facts that, you know, I agree. I'm also interested with the sort of e-power concept as well. But you know, if you're going to operate that type of engine as a compression ignition engine rather than a spark ignition engine, then you've automatically got that bit better efficiency. And I guess with, you know, something like the e-power concept, that the primary energy only comes from the liquid fuel, that's something that's going to be important.
Okay, thank you, Roger.
Okay, thanks both. I believe we have Professor Galton Kagaki raise his hand in the audience. Should we invite Professor Galton Kagaki to answer the question? Professor?
Yes, Galton.
Hi, Galton.
Hold on, let me yeah, can you hear me now?
Yes.
I can hear you, yes.
Okay, well, thank you, Roger. As usual, an extremely slick presentation. But I have a couple of comments. I mean, I just wanted to bring this out. First of all, I think we must keep in mind the size of the problem. The global annual demand for transport energy is around 140 exajoules, which is equivalent to about 4,000 billion liters of liquid fuel. Okay, now we have to sort of be honest and say how much of it can be converted, changed to alternative fuels. I don't think there is much, given the, in the sense it won't be a very large fraction, but given the environmental and energy requirements. Some of them you actually addressed in terms of going to hydrogen or e-fuels and so on. So we are all very fond of saying this is going to be very challenging. And I have always argued that it's not only just challenging, in some cases it's impossible. You know, we need to understand it. But of course, we have to start working on the research and development of this area. I mean, no question. Otherwise, we won't make any progress. That brings me to the other point, I mean, which you covered in your second part of the talk, which is R&D in engine technology. I think there is a lot of scope for significant improvements in both efficiency and emissions in engine technology, some of the things that you addressed. But this brings me to the main point, which is a bee in my bonnet, which is that in many countries, UK in particular, they're planning to ban the sale of internal combustion engines by 2030. And Shell UK are supporting this, basically. What does this mean? This means that maybe by 2027, any global improvements in internal combustion engine in terms of efficiency and emissions will be denied to the UK market because they can't be sold here by 2030. And by 2030, very large majority of cars will still be running on internal combustion engines in the UK. And secondly, the kind of R&D that you're describing will simply disappear in the UK by 2025, because most of the UK manufacturers will get out of ICE vehicles, and very, very talented people who are working and in R&D in this area will lose their jobs. So it does not make any sense to ban internal combustion engines sales by 2030. May I point out that this ban also includes hybrid electric vehicles as well, which is even more stupid in my opinion. Anyway, I'm giving a lecture here, so I'll stop. Thank you.
No, thanks, Gautam. I mean, what I would say to that is that this is a kind of hard truth that we got in some of our calculations on looking at PTL, that many people will say, okay, you know, PTL is a panacea and would allow us to carry on using internal combustion engines. But the amount of energy that you effectively waste in creating PTL fuels and then combusting them again is massive compared to the advantages of just using green electrons in a battery electric vehicle. So I think that that is a kind of uncomfortable truth that we face, and I understand exactly the point that you're making, and I would say also that that in the UK, as I mentioned also, the number of passenger cars is likely to probably reach 2 billion by 2050 from where it is now. So by 2050, globally, there could still be a similar number of passenger cars with internal combustion engines, albeit possibly as part of a hybrid, as there are today. So I don't think internal combustion engines globally for passenger cars are going to disappear anytime soon. And I would say also that we're talking here about passenger cars, that I think that they are arguably the easiest to electrify segment of mobility. When you talk about off-road, when you talk about heavy duty, then when you talk about marine and aviation, electrification of those segments is really, I think, extraordinarily challenging. But I think coming back to our scenario work, it's just really looking at what needs to be done in terms of reaching, of not breaching 1.5 degrees C. And we do need, in areas where it can be achieved, we do need to have to do basically everything. And part of that is a rapid transition towards people using battery electric vehicles for passenger cars. And I know that's slightly uncomfortable, and I find it kind of personally uncomfortable as well. However, I think that it's important to also that there are all the other segments of mobility, and then there's the kind of also the rest of the world as well. And I think it will be, you know, incredibly challenging. But I think that if there is an early target that the UK might have for banning internal combustion engines, and I'm not sure, you know, I do think that it will really drive the transition, because I think, you know, people do feel uncomfortable with such an aggressive target, and I'm sure there are many people here who do, but it's hard for me to see how, unless you do that you can really claim to be serious about the energy transition and doing what needs to be done to prevent warming exceeding 1.5 degrees C.
Gautam, this is a good question.
Yeah,
about the position
may I just
of your
comment
company with banning of internal combustion engines, as asked by Dr. Chow. In fact, I see in the audience Martin Gold, Dr. Gold is from BP. I wonder whether Martin have any comment on the position of, from point of view of BP, about the role of internal combustion engines. Martin?
Maybe Martin is not responding. I think Professor Kakagi, you have further comments or before Martin can join us.
Okay, I just wanted to point out, I mean, in the UK, for instance, if you want to go to zero carbon by 2050, even if you assume that we will need to replace only 60% of fossil fuel use, current fossil fuel use, by non-CO2 means. I mean, we assume that 40% is saved by, you know, lifestyle changes, efficiency improvements, you know, more cycling, more walking. I mean, whatever these people actually suggest. So even if we replace only 60% of fossil fuel use, the UK will need to build about 121 gigawatts of fossil fuel, CO2-free power generation. That is about 41 nuclear power plants. So we have to build 41 nuclear power plants between now and 2050, and at the same time, dismantle existing energy systems. That is, replace 26 million gas boilers. Plus, you know, take out all the non-battery electric vehicles and hydrogen vehicles off the road, and many, many, many other things. If we are serious about this, you know, proper engineering targets have to be set in the short term. For example, we have to say in the next 10 years we'll build 30 nuclear power stations or 33,000 3-megawatt wind turbines. You know, this is not, it's very easy to set targets. Coming back to the UK numbers for electric cars, you know, last year in the UK, they sold 37,800 battery electric vehicles. Even if you assume that by 2030, it increases, and there are about 100,000 battery electric vehicles now. So if you assume that we increase it by 100-fold and go to 10 million, which is extremely, it is impossible in my opinion. It cannot happen in the UK to go to 10 million. But that contributes only 27% of the light duty vehicles. And as you said, most of them will still be running on internal combustion engines, but they'll be condemned to run on technology that is frozen at maybe 2027. So even if the battery electric vehicle is to be promoted, or hydrogen is, there's absolutely no sense in banning the sale of new. By the way, it's not banning all ICE vehicles, it's just the sale of new electric vehicles, new ICE, including HEVs, by the way. It just does not make any sense.
Well, I mean, I think that achieving net zero by 2050 is itself a very ambitious goal. And I think that Shell's scenario work has shown that, you know, I think that obviously different parts of the world will achieve that, need to achieve that by different timings. But if we are serious about achieving net zero in the UK by 2050, and obviously you've got the Green Deal in Europe as well, that we do have to do some things that are fairly dramatic, to be honest. And I think, you know, this is one thing that's been very useful with the Sky scenario, is that it actually kind of shows what actually needs to be done. And you know, the truth is, you need to do a bit of everything, and you also need to be pragmatic as well, because I think it's important. That's why you know, the nature-based solutions, planting trees, can make a really, really big difference. And often I think people often underestimate how important that is. And so the Shell view is that you've got to do things like that, and Shell's getting seriously involved in that type of activity, as I explained. There's also the question of, do things have to be green or blue? And this is a debate that's going on as to whether you should have green hydrogen, which is obviously desirable, but then if you're going to say, well, okay, it's okay to have blue hydrogen as well, that's another way of having effectively of moving towards zero CO2. It just means that you've captured the CO2 and you've sequestered it or utilized it. So I think you need to be a little bit more broad-minded. You need to allow nature-based solutions. You need to say we can have blue electricity and blue hydrogen, as well as green electricity and green hydrogen, and all of these other things. And I think that only by pulling all of these levers can we hope to get there. And I think this is perhaps in some ways where Shell would take issue with some of the NGOs who insist on everything being based on green hydrogen and green electricity. That things like nature-based solutions, things like carbon capture, utilization and storage do have important roles to play. And I think we can't ignore those. And you've got to have this kind of joined up approach if we're serious about doing these. And I mean, yeah, you're absolutely right. It does require an enormous amount of electricity. And I say whether nuclear is the way to go, I personally have my doubts there, but it may also be possible to use it, and also if you're going for a renewable electricity-based system, you always have the classic problem of intermittency and backup, and this is where just being able to store energy chemically is also really important. And there are lots of discussions at the moment about what role could things like ammonia play, and that's certainly being talked about in the marine area. So yeah, I mean, you're absolutely right that what we're talking about is very profound and very, very difficult.
Okay, thank you for a comment. I think we have Dr. Ivan Song here. Dr. Song, do you have any questions or comments on this topic?
Yeah, okay. And generically, sometimes I think, so the previous revolutionary improvement in internal combustion engine was the electronically controlled common rail injection system. Yeah. Sometimes I'm thinking, if it's possible at all, the next revolutionary improvement would be fuel. Now, and so people are working on fuels like biofuels, and also like the ethanol injection, like Roger mentioned, presented. I'm thinking even if it's possible at all to do more, to do the fuel pretreatment by some additives, to maximize the thermal efficiency and also minimize like NOx emission from the engine combustion. Is that possible at all?
I think that I mean it is possible. I mean, for example, using Shell GTL fuel, which being paraffinic does intrinsically give lower PM, and depending on how you organize the engine with a NOx particulate trade-off, it puts you on a different point on the NOx particulate trade-off. And I think also that engine cleanliness is also very important in reducing emissions, and certainly that there is a big link with PN emissions in direct injection vehicles with injector cleanliness, as some of the work we've done with Hongming has shown. That the challenge I would have really is just seeing what difference the fuel can make compared to the generation of emissions control, that it's very hard for fuels to make a kind of step change that you would get in, say, going from Euro 3 to Euro 4. I think to some extent what the fuels have to do is they just have to facilitate the next generation of after treatment systems, and to make sure that they're compatible with them, really. Because if you get to Euro 6D, you have got things that are extremely clean, and you are getting to a situation in some instances in which the emissions, tailpipe emissions, are close to the sort of ambient air quality. So so I mean yes, it's important, and I think that generally air quality is perceived by the people probably to be arguably as big an issue as CO2. But I think from a fuels manufacturer perspective, all we can really do is to just make sure that our fuels do facilitate the most recent generation of after treatment systems.
All right, and so further question is some like oxygenated fuels. Yeah? Different fuels could have like a different carbon hydrogen ratio and carbon hydrogen bond, like single bond or double bond, and backbone chain length or extra. And that would result in different the heat values, heating numbers, or other properties of the fuel. And those properties could make a difference in ignition delay, flame development speed, sorting behavior. And then we could have different trade-offs, trade-offs between NOx and particulate, and NOx and fuel consumption. I don't know if by now, because before I involved some little bit such research, but in recent years I was not into that. I don't know recently if there is the big improvement or big achievement in the trade-offs.
I mean, I think it's generally true that if you do have oxygenated fuels, that you will tend to have you will tend to have less globally rich regions, and you will tend to end up with lower soot. But I think it's quite interesting that on diesel engines, certainly the actual results in the literature are quite contradictory, because there is some evidence that you do get, in some instances, higher PN emissions with ethanol containing fuels, because the heat of vaporization of the ethanol, which stops the droplets then from evaporating. So it's a kind of double-edged sword, whereas generally they're beneficial. And I agree with you that it's generally true that yes, oxygenated fuels do tend to produce lower soot, but the extent to which they produce lower NOx often then depends on the amount of EGR you use. And as I say, I would also commend the importance of engine cleanliness as well to reduce engine out NOx and soot. So I think that where people talk about, I don't necessarily see there being a kind of step change in fuel production. I see perhaps if something can be produced synthetically. I know people talk about OME, for example, as something that can be produced as a route from PTL fuels. And again, I think the fuels that you produce, they have to, in general, be drop in, because otherwise you end up with this kind of chicken and egg type problem that we talked about earlier, whereby you get this thing that it's difficult for people to manufacture fuels if they're not going to have a market for it, and vehicle manufacturers won't provide the vehicles if the fuel isn't available. So I think largely it's difficult to envisage moving significantly beyond our traditional grades. But the exceptions to that are some captive fleets of commercial vehicles in which this is where for example emulsion fuels were used in the past, that you could create the emulsion and you could then achieve low soot and PM there, but otherwise they've got to be kind of fungible with the rest of the fuel supply.
Yeah, to produce the some oxygenated fuel, like with a higher oxygen content, what about the cost? If the cost is similar to the conventional fuel in the market, and maybe the OEMs can do the calibration change, or in the calibration they can judge so what the fuel would be, and they can adjust the calibration settings automatically for the real pressure, timing, to optimize the fuel in the tank.
And again, it depends on what sort of adaptive control the engines have got. But I think that I'd probably assumed by now that all diesel engines would have pressure sensors in them. But usually, I'm just a kind of, sometimes I'm just a naive fuel scientist with a background as a chemist, and you find that obviously people find other ways of doing things, of designing engines that to control the cost. Whereas I'd assume that there would be all this kind of sensing equipment in engines, but I don't see that increasing so much, that people are finding inventive ways to be able to control the emissions while having a robust system without the cost being too great.
Thank you.
Okay. I think we touched base on the hydrogen a little bit. There's quite a lot of questions raised on the background from our audience about what do you see as the hydrogen in the roadmap to net zero emissions, and then how do you compare, for example, hydrogen dual fuel engines to the other maybe methane and ethanol dual fuel engine?
In fact, to this point, I would like to ask Roger, or actually Dr. Song as well, because you're the engine calibration engineer expert. So the question to Roger, I have seen the complexity of the combustion you introduced earlier, as well as the question from the audience about other options. So how are we going to solve all this, in your view, problem of the cost of the collaboration with different fuels, different combustion mode?
Yeah, I mean, the first thing I think I'd say before this is hydrogen, that there is this tendency just to associate hydrogen with fuel cells, and there's this view that fuel cells are automatically going to be that much more efficient than internal combustion engines. And often the efficiencies you see are for stack efficiency or efficiency with sort of zero power in fuel cells rather than drive cycle efficiencies. And what I do detect amongst many heavy duty OEMs is a lot more interest in hydrogen internal combustion engines as a solution, because obviously, as we've said, heavy duty is something that's difficult to electrify, and I think that too often hydrogen gets associated only with fuel cell vehicles, and yeah, I think obviously there are specific combustion challenges for hydrogen, but also potential advantages as well, that you don't have to worry about soot that you do with other fuels. So it means that you can inject it very late. You do have the challenges of NOx, but then people then will operate often in an ultra lean fashion as well. So I think that hydrogen does have its own issues in operating, but I mean what we could see as well is that hydrogen not just being used in vehicles, but being used to kind of decarbonize some of the grid, some of the electricity grid, sorry, some of the gas grid as well. And then if you have natural gas vehicles as well, that may include an element of hydrogen as well. So yes, I think you're probably better placed to answer the questions around the calibration of engines in the context of hydrogen dual fuel. But all I can say is I know that from some of our contacts, particularly among heavy duty OEMs, there seems a lot more willingness to kind of explore this option than there has been in the past. So I'd be very interested to hear what some of the other panelists feel about this.
Mhm.
Dr. Song, Dr. Zhao, do you have any comments on this calibration aspect of new fuels? What's the impact?
Yeah, like for different fuels, if the fuel has like a different heat value, like our ignition delay or something, you do need the different the calibrations to optimize the engine. So for some fuels could have like the potential for good emission, and but for hydrogen, there is no particulate emission. Yeah. But for other, I'm not familiar with hydrogen, but in general, you do have maybe to adjust. If you use like an internal combustion engine for the hydrogen, maybe the calibration definitely could be different from like the petrol or diesel. Yeah.
Maybe I'll quick comment. The hydrogen is something we take fairly seriously, but I think Roger mentioned earlier about even the Shell scenario look at light duty, perhaps electrification taking more market shares. So the very light vehicle, perhaps electric vehicle, is providing reasonable solution. But when you look at heavier vehicle, SUVs, pickups, and commercial vehicles, if we're serious about the 2 degree or even 1.5 degree, hydrogen got to be part of the solution. Whether to do a fuel cell or burn it in the combustion engine, I think it's still debatable. The heavy duty side, people still look at the burning hydrogen in the combustion engine. I think Ford, as example, still got buses running, running in the internal combustion engine. Calibration, I understand the calibration, yeah, reduce NOx is a challenge, but there is a solution. So it's, it's already been used commercially. Okay.
I think there's another question actually trying to explore the this kind of area in different angle is I think the question from audience is we have different concept of engine high efficiency combustion, like the what you mentioned, the GCI, SACI, and what is the challenge and why what's the resistance of adopting those concepts rapidly to achieve high efficient combustion?
Is that directed at me? I think probably I'm not the best person to answer that question, and I may refer that back to a member of the other panelists. But I think, you know, having been involved in a lot of these projects as well, that often the challenges, it's one thing getting a demonstration on a single cylinder, and then you move towards a bench and you look at cold start, and then you've got the problems of having an actual vehicle operating at the system, and actually looking at the complexity of the calibration and the reliability of the vehicle. And I'm looking at it from the outside, and I'm just aware that, you know, in terms of getting vehicles that work reliably and you know, always start in the morning and aren't then going to have OBD warning lights on under any circumstances. Actually, that challenge of producing the final vehicle is something where I kind of have to admire my colleagues who work in the automotive industry and actually produce vehicles.
Helen and Jing, both from industry, they are still the true industry people. But from my experience with JLR, 6 years in the beginning of 2000s, my feeling that the major obstacle to use this more complex systems, even for high efficiency, is cost. It's the cost and prevented the industry to adapt a lot of available advanced technology. You can't put every available technology into one engine for production. For example, the demonstration by research groups like in Japan, US, to demonstrate very high in efficiency, technically, yes, but practically, that is very difficult. If we put all this available components, control technology, everything into one engine, you can reach or near approaching some dynamic limits of the engine. Am I right, Jin? You are at the front line of engine production.
Absolutely. I mean, I think that's why the first question I asked Roger is, as a business, you got to make a profit to survive. That's just given. I think we always face in this environment of, you know, what's good for society. You know, clearly government as a representative of society come up with legislation. That's the, if you like, the legislation red line. So we have to satisfy three needs. We have to satisfy the customer's needs. We have to satisfy the society, i.e. the government needs through the legislation. And we have to satisfy the company needs, which is to have to make some profit. Which is increasingly difficult with this, you know, the three needs not necessarily aligned. You know, if you for legislation, we keep on putting more cost, but if you sell cars, you know, with a combustion engine, very, very expensive, people actually look at, say, actually electric car now is not bad option. So I have to have the balance of, you know, well, we can't charge customer very high price, but we have to meet the legislation with increased cost, and it still had a big profit for us to survive.
You have two examples. You have a Dyson and a Tesla. Tesla keeping getting more and more money from the stocks market, right? They don't care how much money was spent on production or designing. In the end, as long as they can mass production the high tech end of the product they can sell, then the volume is up, then your cost is down. While Dyson is the other way. So they designed a car cost 150,000 pounds or 1.5 million RMB to as a price. Then and Dyson eventually found it's not sustainable, and they give up. If you look at the car Dyson designed, the electric car, is better than Tesla, perhaps, but the cost is so high. They don't have this billions of money and like Tesla have. So then, and Dyson cannot bankrupt on that, so they give up. So that is an example of why technology is not always practically usable in product. I don't know.
Absolutely.
Agree.
You probably know, and the most of the Chinese colleagues know that a few years ago there's hundreds of new energy vehicle companies. Look at today, more and more pack up, go out of business. So our view is only a handful going to survive. So great produce, you know, those low carbon, whatever, zero carbon vehicles. But how do you make it and make money? I think that's a challenge.
But this doesn't mean that technology research is not is all useless, because the technology we research today perhaps will be reserved for the future. We are not 100% sure now which one will, or engines, combustion engine will still continue as it is. But if the combustion engine will survive or will continue to be used at least as one of the shares of the market, then perhaps this technology will be on the real product in some decades later. For example, UKCSAE was researched 20 years ago with a big thrust of the whole global effort on it. But then after 10 years, it's gone down, almost quite. Now it's coming back again because the people run out of other options. You are forced to reach the limit of the thermodynamics, some efficiency. Then this technology has to be picked up and further polished, put into the product. Okay, I will leave this to others. I think I hope we answer the question from the audience.
Yeah, I think that regarding the technology, one is the cost, like what you talked about, and the other thing is the robustness. So if you use the technology, the principle is okay, but in production, we hope that it behaves quite consistently. I'm not familiar with UKCSAE, and I don't know if UKCSAE is easier to use that, is easy to control NOx, or the peak pressure in cylinder. I don't know. But as June said, the OEMs, the manufacturers, always consider three main factors. The government's regulation is a red line. We have to meet that, satisfy that. Secondly, we need to compromise the customer and ourselves a profit.
Yeah, thanks for everyone's comment. I think there's a lot of mentioning about the legislation. Would you say that a more consistent or long-term planned legislative policy will help those achieving three aspects at the same time, putting from research or OEM position in a more comfortable area?
Okay.
I mean, I would certainly say one of the difficult issues is often the price of carbon, which has been a challenge, because if there's a more realistic, and I know this is really difficult, if you set a more realistic price of carbon, then many more things become possible in terms of facilitating investment. So I would say that's probably the most important thing that can be done to allow the market to really work is the carbon pricing. But I accept that this is difficult for people if they're having to pay more for their energy. So it's a really difficult societal problem. But I would say that that's probably the single biggest thing to do. And I do think that governments do have an important role in this, in steering this.
Okay. Any other ones?
Yeah, Roger, I absolutely agree with you. The carbon price is really important for whether society or company, everyone to try to balance these things. If carbon is very cheap, as you know, people just carry on, use the traditional technology if you like. Even my own company, when I talk about the fuel economy strategy for the last few years, and then that increase the price of the product, clearly it doesn't go a long way. But when the carbon price goes up, in China they got double point system, i.e.,
Yeah.
fuel economy now worth a point. Each point could be thousands RMBs or go even 5,000, even more. The same with California, that Tesla actually make money from some the zero emission points, and if you don't meet enough fuel economy points, you can produce new energy vehicles to gain new energy vehicle point to compensate, or you can buy points. But if there's not enough points, the point actually worth a lot of money. So that make company to invest in fuel saving technology or low carbon technology. So carbon price is actually a key. Thank you.
Professor Shuai, any comment from China?
Hi, Hong-Min. Raj, very interesting presentation. So I would say this new energy vehicle competitor with electricity vehicle is a very hot topic even in China. I think since the government, in China want to use this electricity energy in terms of the energy security. So I don't think Chinese government push this new energy vehicle strongly in the market based on the technology. It is based on the security, energy security. You may know over 70% all your imports relying in China. And this is very concerned. In Chinese government, I think this is the main point for this new technology development very fast in China. This is my understanding. If we discussing technology level, yes, hybrid is very good technology, but if Chinese government support this hybrid technology, no opportunity for electricity vehicle. This is the key point. Hong-Min, right?
Good comment. Yeah, it is a different scenario here. In the Western countries, maybe it's not for resources, but perhaps it's more with environmental protection. But again, partly is driven by the market, where China is one of the biggest market. So if anyone who cannot sell, or the company cannot sell products in China, then they will be not good. So I think that here perhaps has the issue at for both. In the end, for company point of view, it's all one word: profit. Was it? Am I right?
Well, yeah, yes. I think in a very simple way, yes. I mean, there are different motivations, I guess, throughout the world, and one thing that's been raised is where will the lithium and cobalt for batteries come from, which is another question that all these kind of security of supply type things do play different roles in different markets as well. But I think at the end, it will be profit and as you put it, I think which will be dominant.
Okay, thanks everyone. I think that's absolutely excellent panel discussion, and I thoroughly enjoyed that. I'm sure that all our audience and participants have the same feeling as I do. And unfortunately, I think time flies, and then we have to come to the end of this event, our webinar. And just a final reminder to everyone that we do have upcoming events in 2 weeks' time for ADAS topic, and also we have a planned annual conference later in the year. And finally, thanks again. Thanks, Professor Roger Cracknell, for your presentation, and also thanks for all our panelists for the excellent discussion around this topic. Thank you, everyone, and we should close here. Thank you.
Thank you, everyone.
Thank you.
Yeah,
Thank you for
Roger.
inviting me.
Thank you.
Okay. Bye, everyone.
Bye.
Bye-bye.